Lines. In the trigonometry portion of our pre-calculus course thus far, we've used the trigonometric ratios to figure sides and angles of right triangles. And for right triangles, if we have any one of the other angle measures besides the right angle plus the length of one side, we can use one of these 6 trigonometric ratios to solve for the other sides of the triangle. But now we're entering the phase of the class where we're going to learn to solve sides and angles for triangles other than right triangles. More specifically, we'll use the law of sines and the law of cosines to solve for unknown sides and angles of triangles. And in this presentation, we'll explore the use of the law of sines. The law of sines also applies to right triangles as well, but with a right triangle, angles and sides are very easy to find using one of the 6 trigonometric ratios. And here is the law of sines. In any triangle ABC with angles A, B, and C, opposite sides A, B, and C respectively, the following equation is true. Sine A over A equals sine B over B equals sine C over C. So the ratios of each of the sines of each angle to the length of its opposite side, they are equal for every triangle. And I will add here the reciprocal version of this equation, which is A over sine A equals B over sine B equals C over sine C. What we need to solve the triangle sides or angles is this. We need enough of the elements of the equation to create a proportion or equation with one unknown. Let's go right into solving this triangle. This is what's called an angle-angle side situation, or AAS. I try not to get too worried about remembering AAS or ASA or anything, because I think it's just easier to determine if we have enough information to create an equation with one unknown. Angle A is 36 degrees, angle B is 48 degrees, and side A is 8 units in length. We have in this triangle enough information to create an equation with one unknown, and these would be the sine to length relationship of an angle with sides A and B. And our unknown will be side B because we know everything else we need. Which version of the equation should we use? We could use either version, the one on the left or the one on the right, but this one in red on the right might be a little easier with our unknown in the numerator. Here are elements inserted into the equation. We have 8 over the sine of 36 degrees equals the side B over the sine of 48 degrees. Setting about solving for B, we multiply both sides of the equation by the sine of 48 degrees. Now on the right side of the equation, the sine of 48 degrees over the sine of 48 degrees cancel to equal 1. Now we have B equal to 8 times the sine of 48 degrees over the sine of 36 degrees. Now we get out our calculator. Mine is a TI Inspire CX calculator. First, I checked to make sure that my calculator was set to degrees mode rather than to radians. Here is 8 times the sine of 48 degrees over the sine of 36 degrees. Press enter. We get side B equal to 10.1145. So we say that B is equal to 10.1145, and accordingly we label our side B. Next, we calculate angle C by taking 180 degrees minus 36 minus 48 degrees, which is 96 degrees. And we label angle C, measure of 96 degrees. Next, we set up our equation to find the side C. For this, we use the portion of the law of sines equation that relates B over the sine of angle B to C over the sine of angle C. And it's 8 over 36. The sine of 36 degrees equals C over the sine of 96 degrees. To solve for side C, multiply both sides of the equation by the sine of 96 degrees. The sine of 96 degrees over the sine of 96 degrees cancel to equal 1 on the right side of the equation. And we have C equals 8 times the sine of 96 degrees divided by the sine of 36 degrees. And here it is entered in the calculator. Press enter. We get side C equal to approximately 13.5359 units in length. And we label that side length in our triangles at the bottom of the triangle. We now say that our triangle is solved, meaning that we have found all the sides and angles of the triangle. Let's look at another triangle. This is solving a triangle given 2 sides and an angle. We have angle A measuring 26.3 degrees, side B, which is 6 units in length, and side A, which is 7 units in length. let's assess what we have. We have angle A of 26.3 degrees, opposite side A, which is 7. And we also have side B, which is 6. And this means that we have enough information to set up a proportion to find the sine of angle B, which will then allow us to solve for the measure of angle B. And this is the version of, and the portion of the law of sines we'll use. The sine of angle A over the side A equals the sine of angle B over side B. And why is this the ideal version for this situation? Because the unknown we're solving for will be in the numerator, and again that will be the sine of angle B. So the equation is the sine of 26.3 degrees over 7 equals the sine of angle B over 6. Now to set about solving for the sine of B, we multiply both sides of the equation by 6. Then 6 over 6 cancel on the right side to equal 1. So we're left with the sine of angle B equals the sine of 26.3 degrees times 6 divided by 7. So using the calculator, we first make sure we're in degrees mode, then enter the right side of the equation, which is the sine of 26.3 degrees times 6 divided by 7. Press enter. We get that the sine of angle B is 0.379775. So we write down that the sine of angle B is approximately 0.379775. And to find angle B, we take the inverse sine of 0.379775. And here is the inverse sine of 0.379775 entered in our calculator. Press enter, we get angle B equal to 22.3197 degrees. So we write in angle B equals approximately 22.3197 degrees. And we label the triangle as well. Next we can solve for angle C by subtracting 26.3 degrees and 21.3197 degrees from 180 degrees, and we get 131.38 degrees. If we press Control, then the equal sign, the calculator gives us a more accurate measure of angle C, 131.3803 degrees, so we label angle C as well. And set about solving for side C, we use the equation form on the right side where the side lengths are in the numerator. And using this version, we have 7 over the sine of 26.3 degrees equals side C over the sine of 131.3803 degrees. We solve for C by multiplying both sides of the equation by the sine of 131.3803 degrees. And on the right side of the equation, the sine of 131.3803 degrees over the sine of 131.3803 degrees cancel to equal 1. So we're left with C equals 7 times the sine of 131.3803 degrees over the sine of 26.3 degrees. And here's that expression entered into the calculator. Side C is equal to 11.909 units in length, which we write in at the bottom right. And place on our triangle drawing as well as at the bottom of the triangle. And so now knowing the measures of all sides and angles of the triangle, we declare that our triangle is solved. Let's look at another triangle, triangle PQR. Angle P is 24.1 degrees and its opposite side P is 4.2 units in length. We also have side Q, which is 10 units in length. Let's see what we can use. We have side P, which is 4.2, opposite angle P, which is 24.1 degrees. And we also have side Q, which is 10 units in length. And our unknown that we will solve for is angle Q. To solve for angle Q, we're going to use the sine of angle A over the side length A equals the sine of angle B over the side length B. And here's the equation set up. We have the sine of 24.1 degrees over 4.2 equals the sine of angle Q over 10. We set about solving for the sine of angle Q by multiplying both sides of the equation by 10. 10 over 10 cancel to equal 1 on the right side of the equation. And here we have the sine of angle Q equal to 0.972215. And to find what angle Q is from the sine of angle Q, we take the inverse sine of 0.972215. And here is that inverse sine entered into the calculator. I used the ANS feature to put the actual calculated sine with no rounding into the calculator. On the TI Inspire, to get to ANS, press Control, then the negative sign key next to the Enter key in the lower right of the keypad. we get angle Q approximately equal to 76.4621 degrees. So we label angle Q in our drawing as 76.4621 degrees. Now, I have a question. I don't know if any viewers have the same question, but does this angle Q, look like it could be 76.4621 degrees? No, it doesn't. The angle appears to be an obtuse angle, which is greater, or would be greater than 90 degrees in measure. We get to this point on the unit circle, we're looking at the unit circle by rotating up 76.4621 degrees from 0 at the right of the unit circle. Here's what is happening. Here, marked on my unit circle between pi over 3 and pi over 2 is the calculated angle Q, 76.4621 degrees. If we draw a horizontal line at this point, that line goes to intersect the unit circle to the left in quadrant 2. And this point in quadrant 2 to the left has the same sine value as the point obtained by rotating 76.4621 degrees up from 0. And we get to this point by rotating up 76.4621 degrees from 180 degrees, or from the left side of the unit circle. The value of this angle is 180 degrees minus 76.4621 degrees, or 103.5379 degrees. So upon further examination and reflection, we choose the angle in the triangle of 103.5279 degrees. Here is the addition to our triangle in green, showing what the triangle with an angle Q of 76.4621 degrees would look like. This brings us the opportunity to talk about what we call the ambiguous case. We say that this is an ambiguous case because given this angle P of 24.1 degrees with the opposite side P of length 4.2, we cannot positively determine if the angle Q opposite the side length Q measures 103.5279 degrees or 76.4621 degrees. So to solve the ambiguous case triangle, we need clues to help us determine if the angle is acute, that is less than 90 degrees, or obtuse, that is more than 90 degrees. One thing is just what I used, the drawing. I picked the obtuse angle of 103.5279 degrees because in the drawing, angle Q looks to be an obtuse angle. Another clue, and an even better one, since not all drawings are accurate, is an instruction that an angle is acute or obtuse, sometimes stated as less than 90 degrees or greater than 90 degrees. These are the easiest clues to pick up. And finally, if the value of 180 degrees minus the calculated angle plus the value of the original angle is greater than 180 degrees, the value of that calculated acute angle is the only possibility and is not an ambiguous case. Now, having talked a little about ambiguity and having resolved angle Q to be an obtuse angle, let's continue solving the triangle. To solve angle R, we take 180 degrees minus 24.1 degrees minus 103.5279 degrees, which equals 52.3721 degrees. And we appropriately label angle R with the correct angle measure. The only thing left to solve is side R, and for that we set up the proportion R over the sine of 52.5721 degrees equals 4.2 over the sine of 24.1 degrees. Multiplying both sides of the equation by sine of 52.3721 degrees, we get R times the sine of 52.3721 degrees over the sine of 52.3721 degrees equals 4.2 times the sine of 52.3721 degrees over the sine of 24.1 degrees. On the left side, the sine of 52.3721 degrees over the sine of 52.3721 degrees cancel to equal 1. So we have R equals 4.2 times the sine of 52.3721 degrees over the sine of 24.1 degrees. And here it is entered in our calculator. So side R rounded to the nearest hundredth is 8.15 units in length. And here we have side R labeled as well. One thing that you may question is the issue of rounding our numbers to a specific decimal place, since about the only angles and triangles in degrees that round off to the sign of rational numbers are 0, 30, 90, 150, and 180 degrees. We will be dealing mostly in irrational numbers when calculating sides and angles of triangles. In preparation to create this lesson, I watched several videos and consulted a textbook and realized that teachers have different ways of handling rounding. Here's how I like to handle rounding. When we calculate values that will or may be used later in the problem, I like taking an answer out to several decimal places, maybe as many as possible. The reason I went out to 4 decimal places for these angles is while fewer decimal places such as 1 or 2 may be fine for a final answer, premature rounding before a final answer will multiply errors in finding the final answer, so I want my calculations to carry as little error as possible on the way to the final answer. So these 2 angles are rounded to 4 decimal places for the purpose of better accuracy in our final answers. Another thing I like to do, especially when stating my final answer, is to acknowledge that the answer is rounded verbally by saying approximately, or by using the approximately equal to sign to show that the answer is a rounded decimal. This probably is not a real big deal, but as a mathematician I think it's helpful to say or notate something that shows we're conscious that an answer is not an exact answer. Most other instructors appear not to be quite as concerned about this as I am, but that's okay. Let's look at a word problem that uses the law of signs. This problem is very much like one done by one of my favorite YouTube publishers, Al. Al and Dave are holding ropes used to hold down a balloon. Al's rope is 5 meters long and makes a 36-degree angle with the ground. Dave's rope is 4 meters long. How far are Al and Dave apart? Here Al's rope holding the balloon at a 36-degree angle. Now here's Dave's rope that is 4 meters in length. Now for the purposes of keeping track of things, we're going to name the corners of our triangle A for Al, D for Dave, and B for the balloon. And the distance between Al and Dave along the ground we'll call side length little b, because that side is opposite angle B. In order to solve this problem, we'll use this ratio of the sine of 36 degrees to the side of 4 meters and set it equal to this ratio, the sine of angle D over its opposite side, which is 5 meters. And here's that equation. We have the sine of angle D over 5 equals the sine of 36 degrees over 4. Next, we multiply both sides of the equation by 5. 5 over 5 cancel to equal 1 on the left side of the equation. We're left with the sine of angle D equals the sine of 36 degrees times 5 over 4. And going to our calculator, we find that the sine of angle D equals 0.734732, which we write down for reference. Therefore, we know that angle D equals approximately the inverse sine of 0.734732. And with the number stored in the calculator, we can use the ANS option to give us a very exact calculation for angle D. Then we press enter and get 47.2845 degrees. And we write that down. And we label angle D accordingly in our drawing. Now to find angle B, we take 180 minus 36 minus 47.2845 and get 96.7155 degrees. And we label angle B accordingly. And now we can set up the last proportion we'll need to use. We have the side B over the sine of 96.7155 degrees equals 4 over the sine of 36 degrees. And cross multiplying, we get B equals 4 times the sine of 96.7155 degrees over the sine of 36 degrees. And here the ratio is entered in the calculator. Press enter. We get a side B of about 6.76 meters rounded to the nearest hundredth, which we write in below. And we box our answer in as correct. I would like to take note in the calculator view screen of these 3 numbers circled in red. Look how many decimal places they are carried out. I did this by using the calculator's stored number by choosing the ANS feature to use the stored values from one operation to the next. The result of using the stored numbers is that pretty exact numbers were used, and the only significant actual rounding came in the rounding off our final answer, which was 4.76 meters to the nearest hundredths place. I would like to go back to the presentation to where we calculate angle D to be about 47.2845 degrees. As it turns out, there is another angle with a sine of .734732. That angle is 180 minus 47.2845 degrees, or about 132.7155 degrees. And here's the sine of 132.716 degrees, which is very close to .734732. Here's what the drawing would look like. But this drawing that we're showing now doesn't really make sense, in that you would not have two ropes holding down a balloon on the same side of that balloon. So going back to our earlier list, we can add yet another reason to resolve the ambiguous case, and that's when one case clearly makes sense while the others do not make sense. We'll finish with a few multiple choice problems the viewer can use to test mastery. Problem 1. In triangle RST shown below, angle R equals 34 degrees, angle S equals 105 degrees, and side S equals 600. What is the length of side R? Stop the video, then solve the problem, then restart to see if you got it right. Here's the setup. We have 600 over the sine of 105 degrees equals R over the sine of 34 degrees. When we cross multiply by the sine of 34 degrees, this is what we get, about 347.35 units in length. And we circle our correct answer, A. Problem 2. Two lighthouses, D and E, are known to be exactly 15 miles apart on a north-south line. The ship's captain at point F measures angle DFE to be 40 degrees. A radio operator at E measures angle EDF to be 53 degrees. What is the distance of the ship to the closest lighthouse from its location? Stop the video and solve the problem, then restart to see if you got it right. Here's the setup. We have x over the sine of 53 degrees equals 15 over the sine of 40 degrees. Cross multiplying by the sine of 53 degrees, we get about 18.6. And normally we would have to look at segment DF as well, but it should be clear, given the angle, that angle DEF is 87 degrees, that segment EF will definitely be shorter than segment DF, so we can circle answer C as our closest answer. Problem 3. In the triangle ABC shown below, what is the measure of angle B to the nearest tenth of a degree? Stop the video, solve the problem, then restart to see if you got it right. Here's the setup. The sine of angle B over 8 equals the sine of 65 degrees over 9. And cross multiplying the 8, we have the sine of angle B equals 8 times the sine of 65 degrees over 9. And then the angle B equals the inverse sine, or arc sine, of 8 times the sine of 65 degrees over 9. And here it is in the calculator, and we circle our closest answer, B. Problem 4. Juan and Josie are standing at the seashore 10 miles apart. The coastline is in a straight line between them. Both can see the same ship in the water. The angle between the coastline and the line between the ship and Juan is 35 degrees. The angle between the coastline and the line between the ship and Josie is 45 degrees. Which of the diagrams below represents the situation? Stop the video and solve the problem, then restart to see if you got it right. The correct answer is C. This is an ambiguous case, as we discussed earlier in the lesson. In the case of diagram B, the ship will be a lot farther out in the water for it to work out. Problem 5. A communication tower of height h is placed on top of a tall building. The angle of elevation from the observer to the top of the antenna is 45 degrees, and from the observer to the top of the building, 37 degrees. What is h to the nearest tenth of a foot? Stop the video, solve the problem, then restart to see if you got it right. On this problem, we could use the law of sines, as in the others, but don't necessarily need to do so. I will just say the correct answer is D, 61.6 feet. Answers A and B are found by solving for the opposite sides of each of the right triangles, not considering that really the length is the difference between those two lengths. This has been Using the Law of Sines. Thanks for viewing.